Lesson 2 for Unit 11 buffers, common ions. We're going to be looking at the reaction of a common ion with an amine-based compound. So, if we had the conjugate acid of a weak base, we're going to shift the acid-base equilibrium. So we're going to consider a 2-liter solution containing 0.2 molar of this amine compound in water. And here's our equilibrium. Our Kb value is 5.1 times 10 to the negative 6th. So if we add 0.5 moles of the amine compound to the solution, will the pH increase, decrease, or remain the same? Justify your answer. Assume adding 0.5 moles of solid amine salt has negligible impact on the solution volume. What we care about here is the ammonium part, so for now we can ignore the bromide ion. So we're adding this ammonium salt, which means that we are going to shift the reaction in the reverse direction. As we add this, our hydroxide ion is going to decrease. So the reaction shifts in the reverse to consume the ammonium salt. The OH minus is also going to be consumed, so the solution becomes less basic, so pH decreases. Let's now look at calculating the pH of the solution before or adding the ammonium salt. And I'm going to make life easier by shortening this to RNH3+, where R is everything attached to the nitrogen. So here we have the first line of your ICE table. Our initial molarity is 0.20 molar from the original problem. We have none of the RNH3+, none of the hydroxide. Our change is going to be making both of our products, losing some of our reactant. This is going to be approximately 0.20 because our Kb value is quite small at 5.1 times 10 to the negative 6th. So we have x, x. So we are assuming that x is small. And remember, you do want to add that to your answer. So we have that 5.1 times 10 to the negative 6th is approximately equal to x squared over 0.20. When you solve for x, remember that x is your hydroxide ion concentration. And when you solve for that, it ends up being 1.0 times 10 to the negative 3rd molar, which means our POH is equal to 3.00, and our pH, which is what we were asked for, is equal to 11.00. Okay, now we're going to look at calculating the pH after adding 0.50 moles of the ammonium salt to the reaction or to the flask that we had previously. We had 2 liters of 0.20 molar of the, and this should be RNH2, let's get that straight, RNH2, and we had a Kb value of 5.1 times 10 to the negative 6th. So we need to figure out the molarity of the RNH3, so we have 0.5 moles of that, so we'll take 0.50 moles of the RNH3, and that is in 2 liters. And so we're going to find that that is equal to 0.25 moles. So we put 0.25 in here. We say that we have 1 times 10 to the negative 3rd of the hydroxide. That came from the previous problem. We're going to be adding x, subtracting x, subtracting x. Remember, we said that the reaction would shift back towards reactants. We still will have approximately 0.20. This will be approximately 0.25. because this change here is going to be very, very small. And then our answer here, we're going to have 1 times 10 to the negative third minus a very small number. We don't know what that is. Let's have a new variable. We're going to call it y. And that's still going to be equal to our hydroxide concentration. So what we have is 5.1 times 10 to the negative sixth is approximately equal to hydroxide ion concentration times 0.25 over 0.20, and that means that our hydroxide ion concentration is equal to 4.8 times 10 to the negative sixth. Our pOH, we take the negative log, is going to be 5.39. So our pH, that's what the question asked for, is 8.61. Now from the original problem, the original pH was equal to 11.00. So the pH did indeed decrease as you predicted.